Assalamualaikum and hi Dr. ZULAIKHA. I'm SAIDATUL NAZIEHA BINTI AZMAN, number matric CD240062, representing group 6, and we all present about the experiment we have done and understood in topic 5, which is thin cylinder. So this is our group members. First, SITI ZULAIKHA, CD240302, SITI SARIJAH, CD240193, SHAHRIL AIMAN, AD190109, and Ming, CD230321.
Hi, Assalamualaikum. My name is Siti Zulaikha binti ZOLKARNAIN. My matrix number is CD240302. Good morning, everyone. Today I will present a theory that related to thin cylinder experiment. This is to analyze the stress and strain of a thin cylinder that is subjected to internal pressure. We will discuss the key concepts such as hoop stress and longitudinal stress. Thin cylinder are structural components that frequently used in mechanical engineering applications such as pipelines, boilers, storage tanks, and others. For analysis purposes, it is assumed that the wall thickness is smaller compared to the diameter, with a ratio T/D is less than 0.1. This enables the use of the plane stress assumption, where radial stress is considered negligible compared to hoop and longitudinal stress. There are two main types of thin cylinder stresses, such as hoop stress that acts circumferentially around the cylinder wall. Secondly, the longitudinal stress that acts along the cylinder axis. The strain that occurring in a thin cylinder can be calculated using the Young modulus and Poisson's ratio. The primary objectives of this experiment is to analyze the stress and strain in a thin cylinder under both open and closed end conditions. Secondly, is to understand the concept of bicycle stress system and use of the strain gauge. By understanding this theory, we can make more precise design decisions for structures that utilize the thin cylinders. It also provides practical insights into validating the engineering theories that we have studied. Thank you.
Alright, so I'm Tan and I will be talking about the results and calculation. So for the results, we can see that we adjust the pressure, and in return we will get the value of the strain from the strain gauge. And we do it for both the open ends and closed ends experiment. The pressure is in bar, in which 1 bar is equals to 1 megapascal. And I think that's it. Alright, so for calculation, we will be calculating the hoop strain and the longitudinal strain. So to get both strain values, we have to know the hoop stress and the longitudinal stress first. So we will talk about the data extractor first. As you can see, for each value, we got assigned data. For example, for thickness, we got 2.5 times 10 to the power of negative 3 meters. And we got the value of inner diameter, Young modulus, Poisson ratio, and internal pressure. We will be inputting it from the table of results. So we will be using 4 formulas, which is for longitudinal stress, hoop stress, longitudinal strain, and hoop strain. So there are 4 formulas for each. However, for open ends, longitudinal stress is always 0. so we don't need to calculate that one. And but for close end, the longitudinal stress is uh, pressure times diameter over 4 times thickness. Meanwhile, for the stress, longitudinal strain and hoop strain, they are the same, in which hoop stress is equal to uh, pressure times diameter over 2 times thickness. And for the longitudinal stress, which have also got different value, and to be honest, I think you can see it for yourself, which is 1 over the Young's modulus, eh, longitudinal times longitudinal stress minus Poisson ratio multiply uh, the hoop stress. And for the hoop strain, just the formula is same with the longitudinal strain, but with the value of the uh, hoop stress and longitudinal stress uh, change to each other. So here are the result of our calculation. We just input the values and we can naturally extract the values. These are simplified to make it easier to see the results. And this is just for the open ends. Alright, so now is for the closed ends. For closed end, we only calculate for the 30 bar, which is also 3 megapascal, and we will get the value of stress and strain that way. And I think that's it. Thank you.
So, as for observation, this experiment investigate the behavior of the thin cylinder subjected to the internal pressure under both open end and closed end condition. So, gauge 1, we observe gauge 1 aligned to measure longitudinal strain, and we observe also gauge 5 aligned to measure hoop strain. So we observe also the gauge value for gauge 2, 3 and 4 are valued somewhere around gauge 1 and gauge 5. So in open end condition, the cylinder end is not capped, so resulting in no axial forces that are transmitted. So for gauge 1, it show the negative value for strain, indicate the compressive longitudinal strain caused by Poisson effect, while for gauge 5 show positive value for strain corresponding to tensile hoop strain caused by circumferential expansion of the cylinder. In closed end condition, the cylinder end are capped instead of not capped as in open end condition. So the internal pressure on the end cap generate axial forces and create biaxial stress state with two stresses, which is longitudinal stress and hoop stress. So this is resulting in gauge 1 show a positive value indicating longitudinal strain caused by longitudinal stress, while gauge 5 show a positive value corresponding to tensile hoop strain due to hoop stress. So this is a graph for hoop strain versus pressure for open end condition. It shows that the hoop strain is directly proportional to the pressure. So as the pressure increase, the hoop strain also increase for open end condition. Next, this is a graph for longitudinal strain versus pressure for open end condition. We see that the slope is negative because due to the longitudinal strain in negative value, so resulting in the negative slope. But the experimental is closely matched with the theoretical line, conforming a linear relationship. Next, this is a graph for hoop strain versus pressure for closed end condition. So for this specific data, the experimental data is only available at pressure 30 bar, and it is slightly lower than theoretical prediction. If the experiment were conducted at pressure 5, 10, 15, 20, and 25 bar, predicted result would likely to follow the same pattern as the theoretical trend. So this is a graph for longitudinal strain versus pressure for closed-end condition. So same as hoop strain versus pressure for closed-end condition. The experimental data only available on at 330 bar, and it is slightly lower than theoretical prediction. Same also on the hoop strain versus pressure for open-end condition. If the experiment were conducted at pressure 5, 10, 15, 20, and 25 bar, the result would likely to follow the same theoretical trend.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti SARIJAH binti MAKMAR. So I will explain about our discussion for this lab. So for the discussion has two questions that what is different between the open end and the closed end conditions. So for the open end condition, in this condition the ends of the cylinder are free, meaning no axial forces act on the cylinder. The internal pressure causes stress only in the circumferential hop direction, resulting in hop stress. Longitudinal stress is zero because there are no constraints or forces in the axial direction. So for the closed-end condition, the ends of the cylinder are capped and the internal pressure applies axial forces on the end caps. This introduces both hoop stress and longitudinal stress into the cylinder. The cylinder experiences a biaxial stress state with stresses in both circumferential and longitudinal direction. Okay, so for the question 2, which case experience unaxial state of stress and which case experience biaxial state of stress? So for unaxial state of stress, the first is experienced in the open condition. Only hot stress act on the cylinder, making it a single directional stress state. For the biaxial state of stress is experienced in the closed-end condition. Both hot stress and longitudinal stress act simultaneously, resulting in biaxial stress system.
In conclusions, the experiment successfully highlighted the difference in strain behavior under open-end and closed-end conditions, providing a detailed analysis of stress and strain in a thin cylinder under internal pressure. And we were able to compare theoretical and experimental strain values for both conditions, which is gaining practical insight into stress-strain relationships, biaxial stress system, and the mechanical properties of materials such as Young modulus and Poisson's ratio. However, while doing the experiment, some challenges were encountered, and ensuring uniform pressure distributions and accurate alignment of strain gauge was a part of challenging. To address the issues, regular calibration of the strain gauge and pressure system is recommended to improve accuracy. Using cylinders with higher material uniformity can help minimize deviations, while precise and automated data collection system can reduce human error. Last but not least, the experiment was achieved its goals and enabling students to comprehensively analyze stress and strain in a thin cylinder. We understand the biaxial stress system and appreciate the importance of practical experimentations in validation's theoretical principle. Thank you.